All right. Yay. So you guys can see that okay, right? Okay, good. All right, so let's begin. So the idea is today the plan is going to be to continue our discussion of scattering, but to do it with an emphasis on this new concept, the scattering amplitude. That's our big thing for today. And so let's remind ourselves where we left off. What we did was we used the Green's function method to basically solve the Schrodinger equation. And what that did, it allowed us to solve the Schrodinger equation where for energy greater than 0, which are the scattering solutions, and for a Hamiltonian is equal to the kinetic energy plus a potential energy, where of course kinetic energy is our old friend, negative h bar squared over 2m times del squared. And so then we did, I'm not going to go through that Green's function stuff again, but what we did was we, the net result was that the wave function, the eigenstate, that's right here, the eigenstate, the energy eigenstate, the eigenstate of the Hamiltonian can be written like this. Psi k of r is equal to e to the I k dot r plus f of r hat times e to the I k r over r. And I'm going to put a box around that because that's so important. And this is really our sort of our generic, I'll write here, generic scattering solution. And this is really big deal. This is a really important result. And it's kind of really simple, but sort of profound at the same time. And so whenever someone says the word scattering from now on, this is what you should think of, because what we have here is that psi is equal to, we have an incident wave plus a scattered wave. And they both happen at the same time. So we have the incident wave and the scattered wave, and pictorially you can draw that function, and this is how it looks. So the way to think about it is, it's nice to have a picture in your head what it looks like. There's our potential, V of r, our scattering potential, and so the idea is that we have it. You think of there being an incident wave, which is a plane wave that we shoot at the scattering potential, like that, and that has the k incident. That's what this is right here. That's the incident k. And then we have the scattered wave. So you can picture it with these circles. And so that's an outgoing spherical wave. And I'll call it the scattered wave. Scattered wave. And so you can see that the incident wave is this e to the I k dot r. And the scattered wave is this thing f of r hat times e to the I k r over r. And it's important that, to notice that this is kr is not k dot r. Just so you remember. And of course, we have there's a formula for this f of r hat. Oh, and I should also say that a way to think about the geometry is that when we have this variable r, I want you to think of r as pointing to the detector. This is r, and here's the detector, and the detector is at r. And r is equal to the radial component times the unit vector r hat. So r points, r is the, think of r as the location of the detector, but this r hat is a vector that's pointing toward the detector. Okay, so that's, so then if we write this function f of r hat, then this function f of r hat is equal to, and this is what we got from the Green's function technique, we see that it's equal to negative m over 2 pi h bar squared times the integral of e to the negative I k r hat dot r prime times v of r prime times psi of r prime d cubed r. Okay, so that's the definition, that's the formula, and we got that formula from the Green's function. And so that's why we needed to do all that Green's function stuff, was to define this function f of r, which is super important, because this function f of r hat, we call it the scattering amplitude. And it turns out that it is the most important thing, although that's not obvious yet, but it will become obvious later. And so this function is the scattering amplitude. And basically it tells us how much, what's the probability to get scattered into a certain direction. Because remember, r hat is a direction, so it's defined by theta and phi. So f of r hat is really a function of theta and phi. And so you can think of it as giving the probability to scatter into that direction, into the direction theta and phi. Actually, it's not really probability, I should say amplitude. But of course, we all know that probability and amplitude are pretty closely related. Probability is just amplitude squared. So f of theta is the scattering amplitude. It's giving the amplitude to go into a certain direction. Okay, and so now the question is, so now we have now the wave function. We see that the wave function is this incident wave plus some scattered wave. So it's a pretty easy way to write. So even though we went through all this fancy math to get at the actual final form of the solution is pretty simple. We have our incident wave plus our scattered wave. But now the question is, what is the differential what is this differential cross section? D sigma d omega. And because d sigma d omega is really important, this is the most important thing for scattering. Because for scattering, I can say that the number of particles, because remember, the number of particles scattered, number of particles per second that go into the detector is equal to 1 over the luminosity times d sigma d omega, the differential cross-section, times delta omega, the solid angle of the detector. So this is always the most important thing, the differential cross-section. And so what is the differential cross-section? So how do we find it? So what we remember is from this picture, I'm shooting in my wave, my incident wave, and I have my outgoing wave. And so the whole question is, what is going into my detector. And so this is my detector, and it has some detector, it has some solid angle, and it also has some area, and the area of my detector, and my detector is located here at this location, R. And so if my detector has solid angle delta d omega, what is the area of my detector, ds? Can someone tell me?
Would it be r squared delta omega?
Yeah, exactly. Right. Exactly. Because that's the relationship between solid angle and area. Okay, good. And so I'll call this little area. So I can think of a little differential area vector ds that's pointing perpendicular to the detector area in the usual geometry. And so if I have this definition, then we know that the differential cross section. Remember, we've defined it as we originally defined it as 1 over the luminosity times dn d omega, where dn is the number of particles per second going into my detector. But then we converted to quantum mechanics, and then we said that this is equal to 1 over j incident, which is times dr d omega, where this is probability, or I'm sorry, this is that's getting them mixed up. That's particles per second, and this is dr is probability per second. But and we can remember we calculated that using the Bourne approximation and all, Fermi's golden rule and all that. But now we want to figure it out again using this new approach, this Green's function scattering amplitude approach. And so the question is, how do we calculate this differential cross section? And so what we need is this R, the probability per second. And so we already talked about how to get that, because we have J is equal to H bar over 2mi, which is times the psi star del psi minus psi del psi star. And that's the probability flux. So that's the probability flux. And that's going to be probability per second per area. And so if dr is the probability per time, then how do I, and if I know j, then what is dr in terms of j? Where dr is the probability per second that goes into the detector. That's my question. There's a question to you guys. So let's zoom in on the detector. Zoom in. Here's the detector. And this is the way to think about it. I have probability current, J. It's the scattered probability current. I have the probability current that comes from the scattering process, and that J, because remember the incident wave, when I shoot particles at the potential, I think of that as like water through a hose. The incident wave is like probability water being flooded in this direction, and then that water hits the potential and splashes. So I'm asking how much of that water splashes into the detector. That water is actually the probability current, is like, it's like fluid. It splashes and it goes places. So how much of that water per time is going into the detector? Somebody tell me.
Is it J times ds?
Exactly. That's right. It's the scattered J times ds. Exactly, because it's probability per time per area times area gives me probability per time. So that tells me exactly how much probability per time is flowing into that detector, which tells us how many particles are going into the detector. So that's the experimental thing. So that's exactly right. So that means that the differential cross section then is 1 over J incident times J dot ds over d omega. Okay, so now we'll use that, because now we have psi is equal to e to the I k dot r plus f of r hat e to the I k r over r. That's my wave function. It's the incident plus scattered wave, and I have my differential cross section d sigma d omega is equal to 1 over j incident times j dot ds of my detector divided by d omega, and that d omega is the solid angle of the detector. Okay, so then how do I get this? What do I need to do now? Because we want to calculate the differential cross section. We've just gone through all this rigmarole to get the wave function from the Green's function method, and so now I'm asking you, how do we get the differential cross section? What do we do next? I'll give you a hint. We have to calculate something. What do we calculate?
We need to find J, like the amount that goes into the detector.
That's exactly right. That's exactly right. So find J. And we know exactly how to do that. It's not hard. J is, that's a lousy J. Let's do a better one. J is equal to h bar over 2mi times psi star del psi minus psi del psi star. I like saying that. And so all we got to do is calculate that. So let's calculate it. Let's do it. And it's not hard. So first we have the J incident. So to get the J incident, then it's going to be h bar over 2mi times psi incident times del psi incident star minus psi incident star. Oops, I'm getting the stars all wrong. Shit. And so okay, so we got to calculate this thing, and psi incident we know is pretty straightforward. So what is psi incident? Somebody tell me.
The plane wave part of the...
Yeah, exactly. E to the I k dot r. So it's really easy, because we know that the gradient of e to the I k dot r, this is why we love plane waves, by the way. The math is so easy. What's the gradient? What's del of e to the I k dot r? Somebody tell me. Somebody tell me.
Negative k squared times the plane wave.
No, because I'm just taking one spatial derivative, not two.
Okay. Ik times.
Yeah, exactly. I k times e to the I k dot r. Exactly. It's really straightforward. And so that makes finding J incident pretty straightforward. And so if we just plug this in, plug these things in to the appropriate places. And when we get this, we're going to get an answer that you've seen before. H bar k over m. Remember that was like density times velocity. So okay, so that's the incident, J incident. So that was the easy part. And that goes in this bottom part, but now we got to do the hard part. Now we have to find J dot ds. All right, and so now we got to find J, the scattered J. And so to find the scattered J, I have to now, I know what the wave function is. This is the scattered wave function. It's this thing. So now I got to find the gradient of it. We know the wave function, but now we have to find the gradient of it. All right, so let's just plug it in and do it. So it's going to be the gradient of it's going to be the gradient of e to the I k dot r plus f of r hat times e to the I k r over r. So we just got to take the gradient of that thing. Now that first part is easy, but it's kind of a pain. So del psi scattering, it's going to be, so that first part, when that hits that, what does it turn into? Somebody tell me.
Ik e to the ikr.
Exactly. That part's easy. E to the I k dot r. But now it's going to hit this thing. It's like, oh no. So, okay, so this part is harder. But first, I want you to notice something. Let's take a look at the geometry. You know, I have my plane wave coming here, and I have my scattered wave, and then I have my detector. And things going, to get into the detector, you have to go along the direction r, right? Now, notice that theta, the direction theta in spherical coordinates, let me draw it here. If that's my detector, and that's r, then the direction of theta is this way, theta hat. R hat is pointing that way, and theta hat is pointing this way. And which way is phi pointing? Phi hat. I'm doing spherical coordinates.
Into the page?
Is it into the page? Yeah, into the page. That's right. Into the page. So that's phi hat. So that's the sort of the famous curvilinear coordinate system for spherical coordinates that you've all seen a million times. And so the point is that I will ask you a question. If I have probability current that is flowing in the theta hat direction, will it go into my detector? Yes or no?
No.
That's right. Because to get into my detector, let's go back up here. You see that I had J dot ds. And ds is pointing, this is the direction of ds for the detector. And so ds is parallel to r hat. That's right. So to get into the detector, because remember the probability getting into the detector, dr is equal to j dot ds. So to get into the detector, you got to be parallel to r hat. You see that? And that sort of makes sense because it's like if my probability is swirling in the theta direction or the phi direction, it's not flowing outward into my detector. So what that means is that when I take this gradient, this gradient is hard because it has theta, phi, and r components. But based on the argument I just made, what are we going to do with the theta and phi components? Tell me.
Ignore them.
Yes, we ignore them because they go away from the dot product. So that's nice. So when we do the gradient, we only got to do the r hat gradient, which makes it easier. So then we see that, let's see, I'm going to put it here, plus. And now when I do the gradient, what it's going to be is I only have to do the radial part. So it's going to be r hat f of r hat, because f of r hat has no radial component, right? Because it's just r hat. And then I have d dr of the outgoing wave, e to the I kr over r. Okay, so that's what the gradient looks like of the scattering wave function. But now I got to do this derivative, which is a little bit of work. And so after I do that derivative, I see that the gradient of the scattered wave function is going to equal I k e to the I k dot r plus f of r hat times e to the I k r times I k r minus 1 over r squared r hat. All right, that's after doing a little bit of algebra, that's what you get. And so then what we can do is we can then plug into the formula for J, plug into J is equal to h bar over 2mi, blah, 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 plug into that formula, and this is what we get. We get J, the probability current for the incident wave parallel to K is equal to h bar over 2mi. It's a big complicated thing, you know, because I had to do the, you know, psi star del psi minus psi del psi star. I had to do all that. And after doing all that, this is what you get. You get h bar over 2mi times 2ik plus a bunch of stuff times e to the I k dot r. I'm not even going to write it, just a bunch of, just so tedious to write. I'll just call it stuff. Bunch of stuff times e to the I k dot r times r hat plus 2ik over r squared times f of r hat squared r hat. Okay, that's what we get. And so there's a way to think about this. Well, first I just want to say this is just incident. This comes from I gotta, looks like I gotta drink of water. Hold on 1 second. So this thing is just the incident probability flux from the incident wave. But this stuff comes from the scattered wave. But let's take a look at these pieces. So for what we want is J dot ds. We want to know how much of this probability flux goes into our detector. So we can ignore the incident flux because we just want to know what happens due to the scattering. So we have to deal with these two terms. Okay, these two terms, and I'll call them term 1 and term 2. And so let's do term 1 first. And so when you look at term 1, then what you can see is that if this is my phi of r, and if this is my detector, then when I look at term 1, what is the nature of that term? That's probability flux, that's flowing. But can you tell me what is the nature of this term? What does it look like to you? It has an r hat, so it's going to survive the dot product. But what about this part? What does this part look like to you? Can someone tell me?
Looks like the incident plane wave.
Yeah, it's a plane wave. So this weird term number 1, I can dot product into my detector, but let's just take a look at it, because check it out, it's a plane wave. So it's coming in like this, see? But it's gonna, when it hits my detector, a plane wave, remember a plane wave goes, this is a plane wave. Remember, a plane wave has it goes plus, minus, plus, minus, plus, minus. And so this plane wave is going to have wavefronts that go plus, minus, plus, minus, plus, minus, plus, minus. So when I integrate that flux over my detector, what am I going to get?
0.
Yeah, exactly. It averages, term number 1 averages to 0 over the detector. So I can ignore it. So let's go to term number 2, okay? So it's term number 2, and term number 2 is this h bar over 2mi times this thing. So let's find j dot ds for from term number 2. And so term number 2 is going to be, then it's this thing up there, you can see it. And so it's going to give me j dot ds is equal to the j, it'll be h bar over 2mi times 2ik over r squared times the scattering amplitude squared times r hat, and then the whole thing gets dotted into ds. All right, so that's the j dot ds using term number 2, where this is, remember this was my term number 2. And so then we see that j dot ds is equal to, now this is kind of cute. Let's look at this. What's another word? What's another way to rewrite ds? You already said it before.
R squared d omega.
Yeah, exactly. R squared d omega. And so now look, I have an r squared here, but it's going to cancel this r squared. And so then I'm going to have an I up here. It's going to cancel that guy, and the 2's cancel. And so what I'm going to end up with, after canceling all that stuff, and then I'm going to have it's ds is r squared d omega. Oh, actually, there was one thing we were missing. What else is there? ds is r squared d omega times what?
R hat.
Yeah, don't forget the r hat, because now I have r hat dot r hat, which is 1. So now j dot ds, when I do all the cancellation, is just going to be h bar k over m times f of r hat squared d omega. All right, does that make sense? So I did all that. And so now let's plug it all in, because I remember I have d sigma d omega is equal to 1 over j incident times j dot ds over d omega. So let's plug it all in. So j incident, remember that was 1 over h bar k over m, right? That was j incident. And now I got my j dot ds, and my j dot ds is going to be h bar k over m times f of r hat squared d omega, and then the whole thing gets divided by d omega. And so look, oh my God, there's some more cancellations. This guy cancels, this guy cancels. Oh my God, this guy cancels. Oh my God, look at that. And I'm left with this. D sigma d omega is equal to f of r hat squared. Oh my God, that's the biggest OMG of all right there. Look at that. We have the differential cross section is equal to the scattering amplitude squared. And that's the scattering amplitude. And so what that means is that this wave function is really special. Look, this is the wave function of a particle. This is the wave function. If I have energy greater than 0, then this is one possible energy eigenstate, where my particle is equal to an incident wave plus a scattering amplitude times an outgoing wave. And the really amazing thing and the beautiful thing is that the wave function, the eigenstate, has all the scattering information in it. It's so simple and beautiful. I really like it. It's, it's just so simple because the differential cross section is built into the wave function. So d sigma d omega is equal to f of r hat squared. Because remember, r hat is a direction. It's pointing into some direction, theta phi. And so this is this is basically, and it sort of should make sense to you, because the scattering amplitude equals the scattering amplitude, because the scattering amplitude tells me how much of the wave is going in a certain direction. And that's exactly what the differential cross section tells us. They tell us the same thing, so it should be very natural that they are in fact equal to the same thing. They are the same thing. So I really like this result because it takes all this complicated scattering stuff and it just sort of distills it to its simple essence. And it once again shows you the importance of this d sigma d omega, because when you first see this d sigma d omega, it just looks like the strangest thing. I have like a little bit of area divided by a little bit of solid angle. It just seems like a very unnatural, weird quantity when you first see it. But now you can see that the differential cross section d sigma d omega is in fact the most natural thing in the world. It's just telling me how much of the wave function is going into my detector. It's so simple. So I just want you to see that. It's sort of, that's why, and this is a result that we got from the Green's function treatment. And so that's why it's worth it to go through all of this hassle of the Green's function, which is, quite a pain, right? It's like all that algebra and Green's function and, integrals and this and that. And we went through all that math, but we ended up with this very beautiful, simple result. So that's why it's worth going through all that math, because we got the eigenstate, and we got and we see that the eigenstate is completely related intimately to the differential cross section. They are indeed one and the same. So if you have the eigenstate, then all the scattering information is living inside of the eigenstate. So that's really a very important message. Okay. But what's it good for? That's also a reasonable question to ask. Who cares? Who cares? So here's the thing. Okay, so we see we got the eigenstate and we got the differential and we got the we got the differential cross section, but we still have the same problem, because if I say to you, because this is the problem, the problem that we're always faced is we're given a potential, a scatterer. I give you a scatterer, like I say, hey, scatter something off of that bunny rabbit over there, or scatter something off of that proton, or scatter something off of that neutron, or scatter something off that crystal, or whatever. We're always given a potential, and we're going to scatter off of that potential. And then the question that we want to know is, given V of R, then what is the differential cross-section? Because the differential cross-section tells me how many particles are going to go into my detector. And so that's what we always want to know. And so how do I go from here to here? Because what we figured out is that d sigma d omega is equal to f of r hat squared. So I could say, so if you're given a potential and I want the differential cross-section, then what you can say now is you can say, well, from the Green's function technique, I see that the that the d sigma d omega is the scattering amplitude. So all you got, so it's the scattering amplitude. But then you're left with the question, how do you get the scattering amplitude, right? So we're still left with the problem, how do we get the scattering amplitude? All right, so that's still a problem. But we understand now the importance of the scattering amplitude. Hopefully, you have some sense of, that that's like the most important part, the scattered wave. But how do we get it? And you probably remember back here, well, actually, I don't need to go there. I'll just write it all over again. So you know how to get the scattering amplitude, because the scattering amplitude is this horrific formula. It's a terrible, terrible formula. It's the worst formula of all. The scattering amplitude is negative m, and we got this from the Green's function technique. We derived this, 2 pi h bar squared. It's the integral of e to the minus I k r hat dot r prime v of r prime times psi k of r prime d cubed of r prime. And so that is the expression that we have for the scattering amplitude. Okay, and it's not, this is not a very intuitive expression, but it's sort of like, it's kind of like a directional Fourier transform in the direction. What's going on over there? All right. It's a directional Fourier transform in the direction of r hat. So, which is not a very intuitive quantity, but what we can do is we can calculate it nonetheless. We can calculate it. And so let's calculate it, because what we can do is, the thing that made this scattering amplitude so confusing is the fact that it has the wave function living inside of it right there. But what we can do is we can play a little trick. Our trick is that we know the wave function. We calculated that too. We know that psi of k is equal to an incident wave plus a scattered wave. And so we can just plug that in. And you might think that that's cheating, because it's just kind of like the snake eating its own tail, right? Because the scattering amplitude is living inside of the wave function. And so now I'm trying to find the scattering amplitude, which has the wave function, and and I got to plug this into it. And so it seems like a little bit, self-referential. So it doesn't quite seem kosher, but let's just do it anyways. It seems funny But as physicists, we're not deterred by funny looking math. We just do it anyways. Do it anyways. And when you do it, something interesting happens, because when you do it, you get this f of k. Well, what you first get is a really horrific formula, which we can just write down, negative m over 2 pi h bar squared. It's this integral. I have this first term, this funny looking, weird looking plane wave, dot r prime, and I have v of r prime, and then I plug in my wave function, which is e to the I k dot r, evaluated at r prime, plus f of r hat prime, e to the I k r prime, d cubed r prime. Okay, so that's the expression. We're plugging the wave function into the expression for the scattering amplitude. We're just going through the motions. And then, but then something interesting. Well, the interesting thing doesn't happen yet. It'll happen in a moment though. Then we have f of k, the scattering amplitude. Now we see that we can break this into two pieces, two integrals. So let's write them both down. It's going to be equal to negative m over 2 pi. That's a terrible pi. Two pi h bar squared times the integral of e to the negative I k r hat dot r prime, v of r prime to the I k dot r prime, d cubed r prime. And then the second integral is going to be this one. Start it down here because it's so big, negative m over 2 pi h bar squared, e to the negative I k r hat dot r prime, v of r prime times f of k r hat r prime, e to the I k r prime over r prime, d cubed r prime. Okay, that's the scattering amplitude. And we see we have two parts. I'll call it part number 1 and part number 2. Now, this is a horrific mess. And when you look at it, you're just going, oh my God, you know, I don't know what to do with that. But let's make an approximation. Whenever you're faced with a horrific equation, just make an approximation. So let's make an approximation. Can anyone guess what the approximation is?
Are we going to get rid of the second integral?
Yes. How do we do it?
I'm not sure.
Well, you're totally right. What's the approximation? What is the approximation that would get rid of that second integral?
The detector is at a large distance, so the 1 over r is like makes it small or something.
Yeah, that would help. That's true. That's a good point. But that's a good point. Yep, far away helps. So let's write that down. Far away. What else helps?
The potential is probably weak at that point.
Well, no, but this integral also, look at the integral. The integral actually, wait, come to think of it, the far away does not help us. Because look at where the integral is done. The integral is over all space. You see that? So the integral is not necessarily just far away. The integral is over all space. So the far away doesn't help us too much, actually, because as I get closer, then that term actually gets really large. What is going to help us here? What approximation is going to help us get rid of that second integral? Tell me. I'll give you a hint. Consider the potential. What would make the second term go away?
Is it that the potential is really small at that distance or something?
Yeah, except we'll make it small at all distances. We'll just say it's a weak potential. That's the approximation. We'll just say it's a weak potential, because the weak potential helps us in two ways. First, notice that there's a V of R in both terms, right? But the second term has the scattering amplitude. So if you have a weak potential, then the potential is weak. But if it's weak, then the scattering amplitude is what? Big or small?
It's also weak.
Yes.
So then it's like weak times weak, so it's smaller than the first.
Exactly. And you guys have seen this before. When you talk about like perturbation theory, you have like a small parameter, and then you have a small parameter squared and small parameter cubed. And you know that as you start multiplying them together, they get smaller and smaller. So this is two weak. So this is a product of two weak terms. And so then for weak potential, then we say that term 2 is approximately equal to 0, and we ignore it. And so now we just have term 1. And so I'll rewrite. And so if I write term 1, then let's take a look at this term 1. And there's something funny here. You see that, do I want to write it again? Let's look at these two terms. We're doing an integral, and you'll notice that we have here, what is this k? First, let me draw the wave, the psi. Okay, that's the psi. I have a, okay. And what is this? And then I have a detector. Remember the geometry? And the detector is sitting at R. And R is equal to R hat R.
Is it the same? Is it like K equals K R hat? Like, is it the same as the other one?
Wait. They're different. So here, do you see what I'm saying? I got a K here, and I got a K R hat here. They're different, see? They're pointing in different things. So which way are they pointing? This one here, K, that's like the easier one. Which direction is K pointing? The one on the right. What direction is it pointing?
Radially out.
The one, no, because look at my picture here. This is the scattering picture where I'm drawing this arrow. See that? Look at that picture and tell me what direction is K pointing?
The detector.
No. When I'm looking at this picture, see, here's the detector up here. Detector. And here's K. See, K is right there. Is K pointing at the detector?
Oh, to the potential, to the target.
Right. Right. It's coming at the target. And it's the initial thing that I'm shooting at the target. And do you remember what we called that? Well, we can call it whatever we want, but I was calling it the incident wave. It's the incident, right? It's the incident wave, which I can also call the initial state, the initial wave, because initially the particle's coming at the potential, but then it scatters. So now let's look at this second term. here, kr hat. What the hell is kr hat? Kr hat. What the heck is that? Kr hat.
Is it like part of the wave that was originally pointing? It's the wave that the detector reads that was originally in the k direction?
It was in the k direction, but now it's pointing in. So what direction is it pointing? Kr hat is pointing in what direction?
To the detector.
Radially out.
That's exactly right. And we've seen this before. Let me redraw this picture. Check this out. Now maybe you'll remember it better if I draw it like this. Remember back in the early days of these lectures, these scattering lectures, I would draw this, V of R, and I said, look, K incident or K initial, and then I did this. Now we draw a detector, and I drew this. It's the same drawing. And what did I call this K? The one going into the detector, what did I call it? Do you guys remember?
K final.
That's exactly right. That's exactly right. I called this one K initial, and I called this one K final. And so what is this? Kr hat is what's, so what is Kr hat? What's another word for it?
K final.
Yes, K final. So now let's do this. Let's plug that into these things. Let's call this guy K initial. And let's call this guy K final. And now let's just rewrite that equation. Because using this definition, if I rewrite that equation, then I have F of R hat is equal to it's going to be equal to negative m, and I should say approximately, because I made the approximation of weak scattering, 2 pi h bar squared e to the minus I k final dot r v of r prime times e to the I k initial dot r prime d cubed r prime. This should start to look really familiar, because this, what is this quantity here? What is it? You've seen it before, tell me.
It's like the change in momentum or something.
It is related to the change in momentum, that's right. But notice I have a wave function on the left. I'll call that
Oh,
psi.
it's like the inner product, like the.
That's right. Although we don't say inner product, but that's correct. That is correct. But what do we call it? What is the
Matrix element?
Like
yes?
the expectation, yeah.
Yes, like the expectation, but expectation is when you have the same wave function on both sides. That's why we
Oh,
call
yeah.
it matrix element and not expectation, because they're different on the two sides. So it's the matrix element of what? Matrix element of what?
V of R when this for the states like K final, K initial,
Perfect, that's exactly right.
which is like the Hamiltonian, right? Like kind of.
It's related to the Hamiltonian. That's right. And so I'll write it like this. So I'll write this K final, the K final state, and then V of R, K initial state. And so that should look really familiar. That's kind of cool. And so that means then that if I have, that means then that remember that d sigma d omega is equal to the scattering amplitude squared, and so that's going to be m squared over 4 pi squared h bar to the fourth, then this matrix element V of R, K initial, K final, squared. So now we have it. Now we have the differential cross-section, which we got using this Green's function technique. And what is it? This answer should look familiar. What is it? Have you, I'll ask you this question. Have you seen it before?
Yes.
Yeah,
And what did we call it?
the Bourne approximation.
Yes, that's the point I want you to see. This is the Bourne approximation. It's the same answer we got before, only it was about 100 times more difficult to get. so I'm laughing, but you're not laughing. Why don't you think it's funny that we just spent like this huge amount of effort to do something that we already got? It's only 1/10 the effort already. So, okay, there's a reason why we did it, okay? It wasn't a waste of time, but I do want to say that this is exactly the same Bourne approximation that we got with Fermi's golden rule. Same result as Fermi's golden rule. We did the Bourne approximation already. It's the same thing, the same damn thing. But there's a reason why we went through all this work, because, and I'll explain why, but well, first, I want you just to sort of bask in the good feeling that, oh my God, it worked. It gave us the same result. That's good. You know, it makes sense. So everything is logical and consistent. You know, yay. As physicists, we like that. We like logical, consistent things that all fit together like a Swiss watch. We like that. But also, what's beautiful is that we got more information now, because remember, for Fermi's golden rule, we only got the differential cross-section. The Fermi's golden rule gave us no insight into the wave function, because the new thing that we got now is that we see that psi is equal to an incident wave plus a scattering amplitude times e to the I kr over r. And so now we also, so not only do we have the differential cross-section, we also have the scattering amplitude f. So that's a new thing that we got from this technique. And second, we figured out the connection between the scattering amplitude and the actual wave function. So that's new. We could not get that from Fermi's golden rule. Fermi's golden rule gave us no insight into the wave function. What is the structure of the scattered wave function? Fermi's golden rule didn't really tell us that. But now we see what it is. And we see how intimately it is related to the differential cross-section. They are literally one and the same. So that's a beautiful insight. And that insight itself is worth all of that hassle of all that math, you know, that we did all that Green's function stuff. And so what we've learned is this relationship between the wave function and the differential cross-section. Now, okay, so that's great. And so that's really cute. But what it doesn't do, I should further say that if we want to find the total cross-section, now we have now we also see that to get the total cross-section of some scattering is just going to be the integral of the differential cross-section d omega over the solid angle. And so that's just going to be the integral of the scattering amplitude squared, right? So these are all relationships that we now can see very clearly. We can see the relationship between the differential cross-section and the wave function, and how the wave function is related to the total cross-section. We see that they're all connected through the scattering amplitude. So that's a beautiful insight, but we still are left with this feeling, but we still are left with this sort of empty feeling, because in terms of actually calculating things, we haven't really made any progress. Because what we have figured out is that d sig, you know, remember the fundamental scattering problem is this. Someone says, here, I'm giving you V of r, and what I want you to tell me is what is the differential cross-section. because the differential cross-section tells me how many particles go into my detector, and I want to know how, you know, how fancy of a detector do I need. And so this is really the question that physicists are always being asked. How, you know, given this potential, how do I relate the differential cross-section, which is what we measure, the number of particles that we measure in our detector, how do we relate that to the potential, the actual physical process, the potential that's giving rise to the scattering. So that's what we always care about. And so in terms of this fundamental question, we have made zero progress, big zero, because we just got the same answer as before. We see that d sigma d omega is equal to m squared over 4 pi squared h bar to the 4th times this. This is basically the Fourier transform of our potential, right? So that's the same thing. So that's the same technique that we already figured out. So in terms of calculating, in terms of relating these two things, we have made no progress because that's just the same formula we already knew. So, but it turns out that that's actually not true. It turns out that we have made a huge amount of progress, but it's just hard for you to see. It's hard for you to notice. It turns out that we have a whole new way to calculate a whole new way. This gives us a whole new way to find the differential cross-section. And why is that important? Why is that important? Well, the reason it's important is because the assumption that went into because the approximation that went into the Bourne approximation was what? What was the approximation? Remind me. Remind me.
A weak potential?
Yes. And now let me ask you a question. Is the potential always weak? Yes or no?
No.
That's right. Many times the potential is very strong. And so the reason it's important is because often we have strong potentials. And what's the simplest example? The simplest example, which is really a trivial potential, simplest example, and I already showed this to you, is the hard ball, the hard wall scatterer, hard wall, or hard ball. Let's not say hard wall, let's call it, say hard ball, because it's a little hard ball. Hard ball scatterer. So if this is so suppose I have a little hard ball that has radius r0, and I'm shooting a wave at it. I'm shooting a particle at it. I know from my Green's function technique, I know that that this is what the wave function has to look like, right? So I know the structure of the wave function, but the problem is that if I try to calculate it, I see that it's infinity for r less than r0, and it's 0 for r greater than r0, right? That's the hard ball. But if I then try to calculate that integral, kv, k final, k initial, you know, if I try to calculate that, e to the negative I, k final minus k initial dot r, v of r, d cubed r, if I try to calculate that integral, what do I get? Somebody tell me.
0 and infinity?
Yeah, well, if I take 0 and add it to infinity, what do I get?
Infinity.
Infinity, yeah, because we're adding everything up. So it's, you know, integral adds everything up. So yeah, it diverges, it's infinity. And so the point is that this is a trivial situation. I just have a hard ball scatterer. And you guys remember, like, the particle in a box was like the easiest problem in the world to solve. This is basically the inverted particle in a box. This is particle out of a box. Particle out of a box, get it? It is. This is the particle out of a box problem. And if the particle in a box problem is the easiest problem in the world, then the particle out of a box problem should also be super easy. But as you can see, the Bourne approximation fails miserably. So scattering off of this most trivial potential is impossible. I have no idea what the answer is. The particle in the box, I'm sorry, the Bourne approximation completely fails. Bourne fails. Okay? So the Bourne approximation fails. So what do we do? So what do we do? Well, we need a new approximation. We need a new technique. So we need a new technique to find the differential cross-section. Okay, so this is my question then. This is this is the motivating question. The motivating question for this section now, for what we're about to discuss, the motivating question is what is d sigma d omega, the differential cross-section for a hard ball? A hard ball potential. Okay, I shoot my particles at a hard ball potential, and what is the differential cross-section? That's my question. Okay, that's the problem that we want to solve. Okay, and so we see that Bourne approximation fails, so that won't work. So that means that the Fermi's golden rule, which is the Bourne approximation, fails. Fermi's golden rule won't give us the answer. The Bourne approximation won't give us the answer. So what do we do? And the short answer is, you know, we have no idea what to do. We're lost. Everything has failed us, and so we have to basically develop a whole new technique to calculate the differential cross section. And that new technique, and this new technique was invented by some smart person. I don't even know who invented it. Some super smart person. This new technique was invented exactly to deal with this kind of situation. And this new technique is called, can anyone, does anybody know what it is? Can anyone guess?
Partial wave analysis.
Yes, the infamous partial wave analysis. Partial wave analysis. I remember the first time I saw partial wave analysis. Oh my God. I just found it to be the most confusing thing in the world. I hated it I don't even know if I ever saw it as an undergrad. I think I did. I can't even remember, but I know I definitely looked at it in graduate school. And the first time you see it, it's not very intuitive. But my personal experience with partial wave analysis is that as I then went off, you know, doing research as a condensed matter physicist, it turned out that the partial wave analysis was all over the place. Everywhere I turned, there was partial wave analysis here, partial wave analysis there, and then it turned out that in my own research, partial wave analysis turned out to be like the most important thing. And that often is what happens, is that the thing, this is one of my rules of physics. The thing that you understand the least and that you find the most confusing will, without a doubt, become the most important thing to you in your research. That always, without fail, always works. The thing that you understand the least and are most fearful of and most confused by, that thing will certainly become, at some point, the most important thing. So with that in mind, let's do partial wave analysis. Okay, so and the thing about partial wave analysis is that when you first look at it and first see it, it's not very intuitive. It's sort of weird, but there is actually a simplicity and a beauty to it. It's very, you know, so my goal is to try to get you guys to see the simplicity and beauty of the partial wave analysis, because now, you know, for me, 30 years later, I think it's really cool and I really love it. And I think it's simple and beautiful and, you know, really, really a neat thing. But I do remember seeing it for the first time and absolutely hating it. So I will have some pity on you for when you first see it. But I will try to explain it to you better than it was explained to me. Because whoever explained it to me really sucked and it made no sense. Okay, so let's do the partial wave analysis. And so here's the thing. We're going to have to sort of build up the partial wave analysis. We're going to have to come at it at a glancing angle and sort of build our way up. But let me give you the sort of the fundamental crux of the partial wave analysis. So we have our wave function, our scattering wave function, and I won't even say wave function. I'll just say it's the eigenstate. Our scattering eigenstate is psi is equal to a plane wave plus this scattered part, this outgoing spherical wave, the outgoing scattered wave. Okay, that's the outgoing scattered wave. And so if I graphically represent this eigenstate, then this eigenstate is, I can think of it as an incident wave, right? K incident plus the outgoing scattered wave. That's how I graphically represent these two parts. I hope this picture makes sense to you. If it doesn't, you should definitely, ask me about it, like what it means. But I have an incident wave and my outgoing scattered wave. And so the whole partial wave analysis is based on the fact that I can take this thing, this object, it's a mathematical object, and I can rewrite it. I can do, it's a math trick. And the math trick, in some sense, is really sort of, you think of it, it's really a change of basis. Because these scattered states, these form a basis. We call this the scattering basis. Each of these eigenstates is, I can think of as a basis state, right? Because, it's a basis, a set of states that are complete and orthonormal. So the scattering states are an orthonormal basis. They're complete and they're orthonormal. They're a basis. But there are other bases around. And so there are other bases. And you have seen them already, because you know that if I have a spherical potential, V of R, and it's spherically symmetric, then you know that there's got to be other bases. You did it even last semester. You guys already know that there's a spherically symmetric. There's spherically symmetric eigenstates. Spherically symmetric states. Let me ask you a question. Is the scattering state spherically symmetric? Somebody answer.
No, it's not.
That's right. It's not. And yet it is an eigenstate of a spherically symmetric potential. That's kind of interesting, but it is. It's an eigenstate. It works. It solves the Schrodinger equation. We figured it out using the Green's function method. It's a solution. So just because you have a spherically symmetric potential does not mean that your eigenstate is spherically symmetric. So I have this, so for the spherically symmetric potential, we've been talking about this eigenstate. I have it right here on the board. You can see it. I wrote it down, the scattering basis, but it's not even spherically symmetric. So it's a pretty complicated eigenstate. It's like, why did we choose that eigenstate? Well, the reason we chose this eigenstate is because of the beautiful relationship between differential, well, I don't want to junk up this too much, but there's a beautiful relationship between F and d sigma d omega is equal to f squared. So the scattering basis is a very useful basis, because if we can write our solution in terms of the scattering basis, then the differential cross-section is built into the eigenstate. So it's a very useful basis. But it's actually kind of a complicated basis, a confusing basis. Because, you know, last semester when you took quantum mechanics, when you guys were given spherically symmetric potential, you guys did calculate the eigenstate. You did it for the hydrogen atom. You also did it for like the free particle, and you also did it for particle in a spherical shell. I know you guys all did that in some class, you know, spherical box. You guys all did the spherical box. And when you did that last semester, if last semester someone was to give you a spherically symmetric potential, then you would calculate the eigenstate. And let me ask you, were the eigenstates spherically symmetric, yes or no?
Yes.
Yes, that's right. Because it makes sense. If someone gives you a spherically symmetric potential, shouldn't the eigenstates be spherically symmetric? Well, sure, of course, that's like the simplest thing to do. But it turns out that but that's a separate basis. Spherically symmetric wave function is another basis, because you guys already know that often you can have a Hamiltonian, and there are different solutions. There are different states that solve the Hamiltonian. So you can have different bases. You can have a change of basis. And so the whole point of partial wave analysis is that we take the scattering basis, this weird thing that we derived with the Green's function, and we write it in terms of the spherical basis. So this is the scattering basis. And then we write it in terms of a spherical basis. And how do you write the scattering basis in terms of a spherical basis? Oh my God, that's really confusing. But that is the essence of the partial wave analysis. That is the partial wave analysis. That is basically it. That's the whole thing. Because it turns out that in a spherical basis, you can have spherical waves. And the spherical waves can be incoming spherical waves, right? Incoming. Or they can be what? What's the other kind of spherical wave?
Outgoing.
Exactly. No one ever yells outgoing, but they often yell incoming. Okay, so you have an outgoing spherical wave. So this is the incoming, and this is the outgoing. And so the thing is, I can write my new basis, the scattering basis, in terms of the spherical basis by adding up the incoming and outgoing spherical solutions. But there's something special about spherical solutions. They have another quantity called what? If I give you a spherical solution, it has quantum numbers. What are the quantum numbers? And it will be done. I'm sorry for going a minute over, but what are the quantum numbers of spherical symmetric solutions? They have what?
L and M.
Exactly. They have angular momentum. And so to do the full transformation from one basis to the other, we have to add up all the incoming outgoing waves, but we have to add them up for all the angular momentum. And it turns out that there are going to be phase shifts. The outgoing waves have phase shifts. And it turns out that the phase shifts are the most important thing, which is not obvious at all why that would be. Why is that? We're going to figure it out. The most important thing. It turns out that the most important thing is the phase shift of the outgoing wave. So this is what we're going to embark upon. We're going to figure out how to mathematically write a scattering wave basis in terms of incoming and outgoing spherical waves. And in so doing, we will notice that the outgoing spherical waves have a phase shift, and that phase shift is the most important thing, and that phase shift will give us the differential cross-section. It turns out that the differential cross-section is in terms of these phase shifts, and every angular momentum has a different phase shift, and that's why you call it a partial wave, because every angular momentum is a wave. So we have the L equals 0 wave, the L equals 1 wave, the L equals 2 wave, the L equals 3 wave. They're partial waves. The total wave has all of them. That's the partial wave analysis. That's what they call it that. Okay, that's it. We'll actually do it next time. Bye-bye.
Thank you.
Thanks.
Thank you,
Okay.
Professor.
Bye-bye.